Hello, Mr. Betts here. I'd like to take a little time to look at a special series called the Harmonic Series. So this sum right here is representing the Harmonic Series, and this is one that's going to pop up a lot. And I'm going to use it here as a counterexample to the inverse of the nth term test. So remember, the nth term test says that if the limit as n approaches infinity of the terms in a series is not equal to zero, then the series has to diverge. And I think that's pretty intuitive. If the terms aren't approaching zero, then the partial sums cannot be approaching some particular value. A common mistake is to assume that the inverse of this is also true. So if the terms do approach zero, that the series is going to converge. Well, I'm going to use this harmonic series as a counterexample to that and show that this is not necessarily true. And this example right here is going to be one where it's not true. So this is, as you could probably guess, is going to be a divergent series. So my argument is if we add up enough terms in this series, which I'm going to start writing out some terms here, if we add up enough terms in this series, we can make this sum as big as we want. All right, so if we pick an arbitrary number, say I want to make this sum bigger than 100. 100's a fairly big number. I can add up enough terms to do that. If I want to make it bigger than 1,000, I can add up enough numbers to do that. If I want to make it bigger than 1,000,000, I can add up enough numbers to do that. So I'm going to use 1,000,000 as kind of a concrete example here. So I'm going to go through a process here and talk about how we can make this sum add up to more than 1,000,000. We're going to need a lot of terms to do that, but we can get there. So what I'm going to do is I'm going to make this argument by grouping the terms. So one, I'm going to put in its own group. The 1/2 I'm going to put in its own group, and then I'm going to start grouping bunches of them together. So starting with the 1/3 plus 1/4. So my argument here is going to use what's called a comparison test, and I'm going to compare it to a series that is 1 plus 1/2 plus 1/4 plus 1/4. And if we group this the same way, 1/4 plus 1/4 is going to be 1/2. And my argument is that 1/3 plus 1/4 is bigger than 1/4 plus 1/4. So that's the same thing as saying 1/3 is bigger than 1/4. And I mean, you know the decimal expansions of 1/3 and 1/4. So this is 0.3 repeating and 0.25 repeating, so it's bigger. But the idea being here that when we divide by a bigger number, we get a smaller number. So in this series right here, the harmonic series, the 1/3 plus 1/4 is going to be bigger than 1/2. Now I'm going to write out a few more terms here. So plus 1/6 plus 1/7 plus 1/8 plus 1/9. And I have enough here to make my next group. I don't need all that. I'm going to group 4 of them together this time. And I'm going to compare it to 1/8 plus 1/8 plus 1/8 plus 1/8. So that would be 4/8, which is 1/2 if I add all those together. And again, I would say term by term, besides the 1/8, each of these is bigger than 1/8 because each of those is bigger than 1/8 because the denominators are smaller than 1/8. Okay, so in the harmonic series so far, with the first 8 terms that I have, we have a sum that's going to be bigger than 1 plus 1/2 plus 1/2 plus 1/2. Okay, so now I'm going to make the next group. And as you might guess, the next group is going to have 8 terms in it. So this last group had 4, so now I'm going to add the next 8 terms together all the way up to 1/16. And that group is going to add up to 1/2, or at least bigger than 1/2. And then I can write out the next group, which is going to have 16 terms in it, starting at 1/17 and going up to 1/32. And those terms are going to add up to greater than 16 over 32, which is 1/2. And so what's happening here is every time I get another group, I know that the sum of that group is bigger than 1/2. Now, here's where that's important. If I want this sum to be, say, bigger than 1,000,000, then I need 2,000,000 of these groups, and that will guarantee that I have a sum that's bigger than a million. Well, I can get 2 million groups. The groups are getting bigger and bigger and bigger, but every time I get a group, since this is an infinite sum, there's infinitely many terms, I can always get another group. All right, so I have right here, I'm going to call this two groups because that's two halves. So I have two groups plus one group plus one group, plus a group. There's a one there, plus a group, plus a group, plus a group. So I have 2, 3, 4, 5, 6, 7 groups right now. So I know that sum at this point is at least three halves. No, three and a half. There's another group that I know will get me to at least 4. Then the next group will get me to at least 4.5. Then the next group will get me to at least 5. And I can always add another group, so I can always get to the next half, and then the next whole number, and then the next half. And so with 2 million of these groups, I'm going to get to at least a million. With 2 billion of these groups, I'm going to get to at least 2 billion. So no matter how big I want that sum to be, I can get enough of these groups to get bigger than that number. So there you have it. The harmonic series diverges because the sum gets as big as we want it to be.